Now we're going to look at the acid-base properties of ions and salts. So some ions will act as bases. And here's one that we saw in the table of common weak bases, hydrogen carbonate ion. This can accept a hydrogen ion from water, and the result is carbonic acid plus hydroxide ion. This is in equilibrium, right? There will be carbonic acid present. There will also be hydrogen carbonate present. Well, you can't have a solution of just hydrogen carbonate ions, because then the whole solution would be negatively charged. And nature really hates it when you separate its charges, right? It puts them back together. You've seen lightning, right? That is nature resolving a separation between positive and negative charge. Kaboom, right? A lot of energy. So we don't separate charges. If we have a negative ion in solution, there has to be a positive ion in there somewhere. And this is why learning net ionic equations in Chem 1A was important, because we don't want to always have to write those spectator ions, but we have to understand that they are there, right? So how could you get a solution that has hydrogen carbonate ion? Well, you would have a salt, and remember, chemists say salt, we mean ionic compound, not just sodium chloride. So sodium hydrogen carbonate is an ionic compound, and it separates into sodium ions and hydrogen carbonate ions. And I just see that this is a mistake on the slide. Do you see what I'm seeing? This is an equilibrium arrow. That's not in equilibrium. That's an ionic salt. It just dissociates. If I forget what fix 65 means, it means go back and fix this stupid arrow. So if we have a solution of sodium hydrogen carbonate, it produces hydrogen carbonate ions. Hydrogen carbonate ions act as bases. So a solution of sodium bicarbonate or sodium hydrogen carbonate will be basic. And sodium hydrogen carbonate is baking soda. So if you dissolve baking soda in water, you have a basic solution. So anions can act as weak bases. We can think of any anion as being the conjugate base of an acid. So in this previous slide, this is an acid, right? Carbonic acid. This is its conjugate base. So if we think of an anion as A-, that's going to be the conjugate base of the acid HA. Okay? So as an example here, NO3- is the conjugate base of HNO3. Well, not every anion is going to act as a base. And this is because if this anion is the conjugate base of a strong acid, then there is no equilibrium and it cannot act as a base. So the conjugate base of a weak acid will act as a weak base. The conjugate base of a strong acid is going to be pH neutral. The weaker the acid, the stronger the conjugate base. So HCl is a strong acid. So it ionizes and makes H+ and Cl-. So this is the conjugate base of an acid. Could it act as a base? Well, Cl- plus H2O, and that would make HCl plus OH minus. But HCl ionizes completely to chloride. The chlorine does not come back to HCl. This only goes in the one direction. Does that make sense? I know this doesn't look like the opposite of that one. So chloride ion is pH neutral. It does not affect the pH of the solution because it is related to a strong acid. The fluoride ion, though, is going to be basic because its conjugate acid is weak. So here's HF, it's a weak acid. When it dissolves in water, it will ionize partially. Right? So we'll get some fluoride ions, but we're going to have a lot of HF as well. This is going both ways. It's an equilibrium. So if we put a bunch of fluoride ions into pure water, some of them are going to react with, I need to draw this out here. So if we put fluoride ions into water, they are going to attract a hydrogen ion and become HF. But see, these are double-headed arrows. Those reactions go both ways. So fluoride has a significant affinity for hydrogen ions. Chloride does not. You put hydrogen chloride in water and the chlorides and the hydrogens separate out, and they're just like, bye, see ya. They're not going to get back together again. But HF, H and F like each other more. So this is a weak acid. It does not completely come apart. So when this is a weak acid, its conjugate base acts as a weak base. With HCl is so strong that its weak base can't do anything. It's just like completely overpowered by the strong acid. So if this one's weak, that one's also weak, and they'll both do something. If the acid is strong, its conjugate base is not a base. It doesn't act as a base. So this diagram shows conjugate acid-base pairs. And this is trying to show that as the acid strength increases, the base strength decreases. So base strength is going down, increasing going down. So something here like HF, this is a weak acid. Its conjugate base is a weak base. Here we have HCl. HCl is a strong acid. Its conjugate base does not act like a base. It is so weak that it does not act like a base. So there's this reciprocal relationship, kind of a push and pull, or a tug of war for that hydrogen ion. So you could think of it this way. Well, no, don't think of it that way. Sorry. Okay. Classify each anion as a weak base or pH neutral. What we want to do here is we want to find the conjugate acid and see if it's strong or weak. So, what's the relationship between a base and its conjugate acid? H plus. So, I'll take this is the base, and I'll add H plus to get the conjugate acid. Or you could write that as HCHO2. Is this a strong acid? No. And you look at it like this and you're like, oh, that doesn't even look like an acid. Well, we don't even really need to be able to recognize it that much. It's not one of the six, right? So it's weak. So this is a weak acid. So does its conjugate base act as a weak base? Yeah, it does. So this is a weak base. So here we have perchloride ion. What's the conjugate acid? HClO4, right? Is that a strong acid? Yeah. How do we know it's a strong acid? Because I told you. I said memorize this. Strong acid. So does this anion act as a base? No. It's pH neutral. So, it might be helpful, like, I kind of started this yesterday just spontaneously in lecture, and so I'm trying to kind of work it out. I'm always looking for new analogies, new ways to think about it. So this is a strong acid. This guy is so strong, it doesn't let this guy do anything, right? This is overpowering. I'm the acid, you're nothing. Here we have a weak acid. It cannot overpower the weak base, and so they both can act. One is the acid, one is the base. If that helps you remember, great. If not, just erase it from your memory. So we can determine the pH of a solution containing an anion that acts as a weak base, but we need to know its Kb value. So anything that's acting as a weak base, we can do that process. We write the equation, and then we make an ice table, and then we solve for X, right? So what is the relationship between Ka and Kb? Because if you're looking at the conjugate base of a weak acid, you may not be able to find its Kb value. You're going to find Ka for the weak acid. So try to run through this relatively quickly. So here we have an equation representing an acid, right? So Ka is equal to H3O plus times A minus divided by HA. And over here, we have a generic equation for our conjugate base acting as a base, right? It takes a hydrogen ion, produces hydroxide, and regenerates. So this is the equation for Kb. So that's going to be hydroxide ion concentration times HA divided by A minus. I wrote these off-centered on purpose. Here I have A over HA. Oh, I'm sorry, that should be A minus. A minus. And here I have HA over A minus. So what I'm going to do is I'm going to take this equation and turn it upside down. Invert it. So 1 over Kb is equal to 1 over hydroxide ion concentration times A minus over HA. I just took everything that was in the numerator, put it in the denominator. What I'm trying to get is A minus over HA by itself, so I can substitute in over here. So now what I can do is I can multiply both sides by OH minus, so I get OH minus over Kb is equal to A minus over HA. And I'm not going to ask you to do this on an exam. So this is equal to that. Yeah? So I'm going to plug that in. did I have green? So Ka is equal to H3O plus times OH minus over Kb. So let's simplify this. Ka times Kb is equal to H3O plus times OH minus. So the autoionization of water, right? This has an equilibrium constant. And what was that called? Kw. I know, right? And Kw is 1 times 10 to the minus 14. So what we end up with here, I guess let's go yet another color. Ka times Kb equals Kw. That's kind of cool, isn't it? Even if you can't do that on your own, just watching it happen, it's like, wow. I like math. Any questions? So this is something that I believe is on the sheet with useful information for exams. Okay, so let's use that. Find the pH of a 0.250 molar NaC2H3O2 solution. Ka is 1.8 times 10 to the minus 5. So if we take this and try to write the weak acid expression for that, we're going to have problems because there's no hydrogen at the beginning to lose, right? This is an ionic compound. It's got a metal here. And so what is that doing when it dissolves? Well, ionic compounds, when they dissolve, they dissociate completely. And we get these two guys. Do we care about sodium? Not unless you have high blood pressure. Sodium's not doing anything. It was just the partner that came in with the acetate ion. The acetate ion is what's going to do something. This is the conjugate base of a weak acid. It can act as a base. So we can write the equation for that, C2H3O2 minus plus H2O will give us HC2H3O2 plus OH minus. It's all about moving a hydrogen ion back and forth. It's like a game of hot potato or something. You're just passing this hydrogen ion back and forth. Okay? So it can get tedious writing all those letters. And so this is acting as a base, and so we can call that B. B plus H2O is then in equilibrium with B plus OH minus. But since we've got it all written out, I'm just going to leave it there. And we'll just use it. Okay, so ice table. ICE the H2O boxes are not used. So sodium acetate dissolves, separates, and so the initial concentration of C2H3O2 is this 0.25. What's the initial concentration of acetic acid? 0. And hydroxide? 0. Essentially 0. Mm-hmm.
So, always in the product we have plus X, right? I know.
That's a good question.
Okay.
In the products for the change, do we always have plus X? So far that's been the case, but it will not always be the case. Okay.
Should be careful about it.
Yeah, you do need to think about it. You can't just automatically put plus X in the product side, because we'll get to an example, I think today, where it's not the case. But we look at these, they're both 0. We can't go lower. This has to be plus. Right? Plus X and plus X. And this one must be losing X. Oops. It's not what I meant to do. There we go. Saved it. We add those together. We get this. And so we can look at this is HC2H3O2 times hydroxide ion concentration divided by C2H3O2 minus. Does that equal Ka? No, it doesn't. Because this is acting as a base. This is Kb. So a common mistake is to just use the Ka, stick it in here. You can find an answer, but it won't be correct. They didn't give us Kb. You can try to look it up. It won't be in the book. You can find it online, but it won't be in the book. What do? Well, we just learned the relationship between Ka and Kb. So we have to calculate that. Ka times Kb equals Kw. So Kb equals Kw divided by Ka. Kw is 1 times 10 to the minus 14. And Ka is given as 1.8 times 10 to the minus 5. Oops. Wrong button. .555 forever times 10 to the minus 10. Any questions so far? So this is the value that this expression is equal to. So 5.556, times 10 to the negative 10th is equal to x squared divided by 0.250 minus x. I didn't do the x is small check on the previous example. We'll do it here. So this is 0.005%. Is that small enough? Yeah, that's small enough. What do you get from the solver?
785.
11785. Okay. Those guys are really close, aren't they?
So usually when we are doing the small x, we compare the concentration to the Ka. And the base situation we also compare to Ka or to Kb.
Anytime you're doing the x is small approximation, you're going to take what you got for x and divide it by what you subtracted x from. So in this case, it's 0.25. So we take this number divided by that number times 100, and that's what we're looking for to be less than 5%. Is this the pH? No, it's not even the hydronium ion concentration, right? This is the hydroxide ion concentration. So we have to get from hydroxide ion concentration to pH, we have to go around the circle. This is going to happen a lot, going around the circle, right? So I'm just going to shorten this. So pH is 14 minus the POH, right? 14 minus the negative log of, I'm going to put that in scientific notation. Whoops. Doing that mostly because it takes up less space. So 14, whoops, come on. Did you get that number? Is that a reasonable number? Here we have the conjugate base of a weak acid. We've talked about how it acts as a base. So then we expect the pH to be above 7, right? Because it's acting as a base. Any questions? Which of these anions acts as a weak base? What are we looking for? We want to look at their conjugate acids, right? So the conjugate acid for HCl is for Cl minus is HCl, and for Br minus is HBr, and for F minus is HF. So we want to look at what are the conjugate acids, and then in order for this to act as a weak base, should the acid be strong or weak? It needs to be weak. Well, which of these is a weak acid? HF. So this is a strong acid. We can think of it as overpowering that guy and not letting him do anything. HBr, strong acid. It's on the list of 6. Overpowers Br minus, doesn't let him do anything. HF is a weak acid, and so it cannot fully control the F minus, and the F minus gets to act as a base. So those are the anions. Let's talk about cations. Cations can act as weak acids, and there are 3 categories. The first one we'll talk about is cations that are counterions of strong bases. These are pH neutral. So just like with the strong acids, the conjugate does not act as a weak base. Here, the counterion does not act as a weak base. So these are things like sodium. Because sodium hydroxide is a strong base. It ionizes completely into sodium ions and hydroxide ions. So this is strong. This is the counter ion of this base. So it can't do anything. It can't go backwards. So it doesn't do anything. It's pH neutral. So we can take the formula for a weak base and make a cation by adding a proton to it. Right? So here's the base, and now it's got a plus on it. And this is when we looked at weak bases, we said, well, you put them in water, and they'll take a hydrogen ion and leave hydroxide. This is the base. This is the conjugate acid. All right? So this is the conjugate acid of a weak base. It can act like an acid. Again, we're looking at what's the relative, the conjugate version of this. Is it a strong base or a weak base? If it's a weak base, this can act as a weak acid. And then to calculate the pH, we're going to need Ka, which we derive from Kb, like we did in the opposite direction for the weak base. The third group of cations are small, highly charged metals, such as aluminum and iron 3. Aluminum has a +3 charge. Iron has I don't remember what I said there. Anyway, iron 3. Fe has a +3 charge. If we find these on the periodic table, we see that aluminum is in row 3, period 3, and iron is in period 4, meaning they are small relative to the other metals, right? As you go down in the periodic table, atoms get larger. And these have high charges, +3. So these two you need to remember. What these do is they become hydrated in water, and then that hydrated ion can act as a Bronsted-Lowry acid. So it can donate a hydrogen from one of its waters to water and make H3O+. This is going to seem really weird to you and like, where the heck is this coming from? You do not have to understand this at this point. The simplest thing here is remember that Al3+ and Fe3+ act as weak acids. And why is kind of complicated. There are a lot of other times where I say, don't just memorize this thing because it's too confusing. Let's learn the rule behind it. Here, understanding the reason behind it is harder than just remembering. Yeah. As long as I'm at it, I should fix slide 76 also. My animations are broken. Classify each cation as a weak acid or pH neutral. So what are we doing? Well, there were 3 categories, remember? Counter ion of a strong base, conjugate acid of a weak base, small highly charged metal. Well, while it's fresh in our mind, is this a small highly charged metal? Yeah, that's the one of the two I said, let's remember, aluminum and iron. So, is this going to act as a weak acid, or will it be pH neutral? That'll act as a weak acid. Yeah, and the answer is just sitting up there. Well, what about Li+? Is that the conjugate acid of a base? We don't really think of it that way. It is the counter ion of lithium hydroxide. This is a strong base. It ionizes completely. And so it does not let the lithium ion do anything. So this is going to be pH neutral. What about this guy? Well, that doesn't look like the counter ion of a strong base, does it? The counter ions of strong bases have to be metal ions. Well, if this isn't the cation, the counter ion, then it must be the conjugate. So the conjugate, if this is the acid, we're going to lose a hydrogen and get CH3NH2. And you may look at that and say, well, that doesn't really look like anything to me. This is a relative of ammonia. Ammonia is NH3. One of the H's has been swapped out for CH3. We do not recognize this as a strong base. It's a weak base. This is a weak base. This can act as a weak acid. So this cation is acidic. Well, I should say, I was looking up here. The choices are weak acid or pH neutral, so weak acid. Any questions? Yeah.
A,
Mm-hmm.
we're having Li plus
Mm-hmm.
and as a strong base with LiOH. And then the next one, the base lost H.
Mm-hmm.
So how would we know?
Yeah, so what's confusing about this is it's a little bit different than just looking at the acids, right? Because the acids, we just looked at the conjugate acid, the anions. We looked at the conjugate acid to see if it was strong or weak. Here, if we try to look at the conjugate base of Li+, well, what would that be? If this is the acid, then the base has to lose a hydrogen ion, right? This doesn't have a hydrogen ion to lose. So we're kind of stuck there, right? Like, oh, how does that work? Doesn't have a hydrogen ion to lose. Let me pause this. Yes?
What about the B one?
What about the B?
Yeah, like is it losing an H2 also? Or why is it losing?
Okay, so this one, we can write the conjugate base because we can remove an H from this. So the relationship between an acid and its conjugate base, or a base and its conjugate acid, is H+, right? So here, I can remove an H+ and write something. This is a weak base. I can't remove H+ from this because there is no hydrogen, right? Lithium ion cannot act as a weak acid. It can't donate hydrogen ions. But the way the book categorizes them, it says this is the counter ion of a strong base. So a strong base would be lithium hydroxide. So these two don't fit exactly the same pattern, and there's nothing I could do about it. It is a little confusing. Yeah.
So the question was about if it is weak acid or pH neutral.
Mm-hmm.
So you give us acids basically. Is it always when you ask us?
Yeah,
Or acid?
The tricky part is when you're talking about cations. Cations can be acidic or not. And when it's not, they're neutral. Anions can be basic or not. Okay. So the cation one is going to be a little more confusing than the anion one. Basically, take that ion that you're trying to figure out and look at it as what would its conjugate be? I mean, we could write a conjugate acid for this, but that also looks ridiculous. LiH2+. That's not good. So with these guys, you don't really get anything good when you look for a conjugate. And those are going to be pH neutral. If you can write a nice conjugate for it, and the conjugate is weak, then it is going to act like something. Here we see that this is the acid because it has the hydrogen, it would donate, and this becomes the base it could accept. So if this is the thing, that's a weak acid. It is a bit confusing. Okay, so let's just dive into that confusion and think about, well, what if we have both of these things together? An ionic compound, right? You've got a cation and an anion. Cations can be acids, anions can be bases. So what is this solution going to do? Well, we can have salts, ionic compounds, where neither the cation nor the anion acts as an acid or a base. So these are going to be pH neutral. This is where you have that cation being the counterion of a strong base. The anion is the conjugate base of a strong acid. It can't do anything, it'll just be pH neutral. You can have a salt where the cation does not act as an acid, but the anion acts as a base. So here we've got the cation being the counterion of a strong base, and the anion is the conjugate base of a weak acid. So let's just look at KNO2. So what are the two ions there? We've got K plus, and we have NO2 minus. Well, can we write a conjugate base for K plus? Or a conjugate acid for it? No, it doesn't make any sense. Is it the counterion of a strong base? Yeah. KOH is a strong base. So that one's going to be neutral. Here we have HNO2. Its conjugate would be HNO2. Is this a strong acid or a weak acid? That's a weak acid. So can this act as a base? If this is weak, this is also a weak base. So this can act as a weak base. So a solution of KNO2 would be slightly basic because the NO2 minus can act as a base. Okay? Then kind of the opposite, where we have the cation act as an acid, the anion does not act as a base. So here the cation is going to be the conjugate acid of a weak base, or aluminum or iron 3, those small, highly charged metals. And the anion is the conjugate base of a strong acid. So let's do this one. So we have NH4 plus and Br minus. Let's look for conjugates first. Can we write a conjugate for NH4 plus? Yeah. We can take away the hydrogen ion and get NH3, something that is reasonable. So NH3 is a weak base. So NH4 is a weak acid. What would the conjugate for Br minus be? It would be HCl. No, it would be HBr. Is this a strong acid or a weak acid? This is a strong acid. So this guy is overpowering, maybe bullying this guy, won't let him do anything. Here, the partner is also weak, and so they can both do stuff, right? Here, the partner is something that's strong, and so this guy is so weak he doesn't do anything. So this one's pH neutral. So we have the cation acting as a weak acid. We have the anion being pH neutral. So this will make an acid solution. It'll be acidic. This concept is not a huge deal in this course, but it does come up. So I'm not going to say just ignore it, but, you know, you can pass the class without understanding this. And then the last category is where the cation acts as an acid and the anion acts as a base. And so now what we have to do is we have to see, well, which one is stronger? And we would have to compare the Ka of the acid to the Kb of the base. Whichever one is stronger is going to dominate. So this summarizes those different possibilities. This table may or may not be useful to you. I don't particularly find it helpful. Okay. Determine if the solution formed by each salt is acidic, basic, or neutral. So here we have an ionic compound. The first thing to do is to see, well, what are the ions in here? I think writing them down is a good idea. So I've got sodium ion and I've got hydrogen carbonate ion. And then I'm going to look to see what their partners are, or their conjugates. I can't write a conjugate for sodium. And that tells me, well, is this part of a weak base, a strong base? NaOH. Yeah, that's a strong base. So this isn't going to do anything. That one's going to be neutral. So that one's neutral. What about HCO3 minus? Can I write the conjugate for that? Can I add a hydrogen ion or take a hydrogen away? I can add a hydrogen ion and get H2CO3. Is this a strong acid? No. That's a weak acid. I'm going to call this Wa, weak acid. And so that makes this a weak base. So a solution of sodium hydrogen carbonate is going to be acidic, basic, or neutral? Basic. Because the anion acts as a weak base. Let's do this one. This one looks weird. Lots and lots of letters there. We're going to separate things into two ions, one cation and one anion. So don't try to take this guy apart. If the beginning looks confusing, try looking at the end. Can you recognize an ion at the end? Oh, Cl, that's kind of friendly, right? So CH3, CH2, NH3, and we pull off the Cl. So the Cl would be minus, this would be plus. Could I write a conjugate for this? Could I add or remove a hydrogen? I could. I could remove a hydrogen from that. We've got that nitrogen here. This is like ammonia. Ammonia is a weak base, so this is a weak acid. What about chloride? It's the conjugate base of a strong acid, right? So here we've got a strong acid, and so that one's neutral. So I've got something acting as a weak acid and something that's neutral, so this is going to be acidic, right? KNO3. Well, I've got K plus, and I have NO3 minus. Here we get that metal ion again. It's not a small highly charged metal, it's only +1, right? We can't make a conjugate of this, so is this the counter ion of a strong base? Yes, KOH, strong base. So is that going to do anything? No, it's not going to do anything. Let's do this. Well, what about NO3 minus? What's that related to? HNO3. Strong acid? Yeah. This is strong. Because that is strong, this can't do anything. So will this solution be acidic, basic, or neutral? Neutral. One more example. This is iron 3 nitrate. Again, we want to look at the two anions, one cation, one anion, the two ions. One cation, one anion. So we've got Fe3 plus, and we have NO3 minus. Here we've got a metal ion. Oh, that's one of those that we're supposed to remember. Small, highly charged, right? +3. So that can act as something. And so maybe you're like, but I can't remember if it's supposed to act as an acid or a base. Well, let's look at the anion first then and see what the anion's going to do. So this, we can write a conjugate for. You can always write a conjugate acid for the anion, HNO3. So that is a strong acid, which means that this does not act as a base. This is the one that could have been the base, so that means this guy is the thing that could possibly be an acid. So that can't do anything, but this acts as an acid. So this will be acidic. When I look at cations, my mind doesn't automatically say, oh, that could possibly be a weak acid. My mind doesn't go there. I know it's possibly something, but my brain just, I just don't do this part of this lecture that often. But this anion, you can always write a conjugate acid for it. And so that can help you to remember, well, this is the possible base, that's the possible acid. Or I guess you could do alphabetical order too. The possible acid comes before the possible base. Basic, acidic, neutral. Any questions about that one? We got one more and then we're going to stop. Which ionic compound forms an acidic solution when dissolved in water? This is kind of asking it like the other way. Not what are these, but which one forms an acidic solution. So we're looking for something where one of the ions can act as a weak acid. So again, let's look at the individual ions. You got NH plus and Br minus. Which is the possible acid? Well, it's the first one. Because I just made that connection. Alphabetical order, right? Possible acid, possible base. So we're looking at this guy. Well, can I write a conjugate for that? Yeah, NH3. I can remove a hydrogen ion. It's already positive. I don't want to try to put another hydrogen ion on it. This is a weak base. Does this act as a weak acid? Yes, it does. This one, does it do anything? That's going to be neutral because that is the conjugate base of a strong acid. This one's strong, so that one gets canceled. Can't do anything. So here, this is going to act as a weak acid. So that solution will be acidic. Now this said singular, which compound, right? Let's just double check these other two. KCl, K plus, Cl minus. For the positive ions, the three categories were counter ion of a strong base, conjugate acid of a weak base, or small highly charged metal. This is a counter ion of a strong base. So does it act as anything? No. Here's our anion. We can write the conjugate acid for that. The conjugate acid is strong, so this one gets canceled. Can't do anything. So that one would be neutral. Neither of them do anything. And sodium hydrogen carbonate, well, you may remember this one because we talked about it twice today. Here, sodium ion, counter ion of a strong base, right? So that's not going to act as an acid. Let's look at the conjugate acid of this guy, H2CO3. That's weak, right? Weak acid, so this acts as a weak base. But we're looking for something that forms an acidic solution. So this would form a basic solution. Any questions? Yeah.
So usually when we have HCO3 minus, or I don't know, the one that have H, we take out from it.
Okay, so I was kind of hoping nobody would notice that. So HCO3 minus, you could remove a hydrogen ion. This can act as an acid or a base. Because we can write the conjugate acid for it, but we can also write the conjugate base. So acid, base, base, acid. It's amphoteric. So how do we know which one to do in this situation? Well, you can look at the Ka values, or you can think about, well, what do all the other anions do? They're going to gain a hydrogen ion, right, if they're going to function. So we're going to look at this guy gaining, even though we look at him and we see he could lose. But we don't want to overthink it at this point. But that was good spotting that. The anion would always add. So this anion, when we're doing these questions, the anion, you're always looking at it adding.